Dearly beloved, we are gathered here to remember Radio Shack Micronta 12-volt regulated power supply and laser pointer, who gave the ultimate sacrifice in the cause of science and technology. Well, what happened is, as I was doing some more checking around, getting ready to make the next video, when I wasn't looking, something failed in this power supply, and the full unregulated filtered voltage from the transformer came to the output, which was 25 volts, and when I pressed the button on the laser pointer, that put 25 volts on the laser pointer, and so the death of the power supply took the laser pointer with it. So what we are going to do is do a quick autopsy on this power supply. This laser diode isn't really worth trying to do anything with. If you look between the switch and the main module, there's a tiny, tiny little resistor here, and the smoke came out of that resistor. And I don't know if the main part of the module survived. I don't even know if it's worth trying to dissect it. It's just too dang small. It only cost $1. I've already replaced it, and I'm going to buy some laser modules to experiment with further. So we'll just put this aside and move straight to the power supply proper. So here's the basic schematic. I haven't traced the schematic out yet. This is just the basic idea of how it works here. And so there are two possible scenarios for how this failed. One, the Zener diode may have burned open, in which case we have the filtered unregulated power from the filter capacitor going straight to the base of the first transistor, which would turn the transistors fully on and put the unfiltered voltage straight to the output. The other possible scenario is that the pass transistor shorted. So let's poke around with a voltmeter and see if we can get an idea of what happened. So let's go ahead and plug this in and turn it on, because it doesn't smoke at least. Even the little red light comes on. So here's my horrible fright meter here that cost me about $8. I try to use these inexpensive parts just to show that you don't have to make a big investment to learn electronics. So here we go, and we'll check some voltages here. Let me go ahead and get a different probe for the positive side real quickly. Okay, here's the ground over here. Let's take a look at the output. I got over voltage, so let's set this up to 200 volts and take another look. And we have 23 volts. I said 25, but it looks like what we really have is 23. Now let's take a look, and I believe the yellow wire is ground. Let's check it out. Nope, we've got 15 volts there, so that means that the gray wire must be the ground. And there it is. Okay, but tells us something already. If I look at the yellow wire, which is at the cathode of the Zener diode, I've got 15.3 volts. No wonder this thing had it's supposed to be a 12-volt power supply. It was giving me 15 volts. Maybe the Zener diode is out of spec or something, but I suspect it was just a 15-volt power supply for real. So let's take a look at the potentiometer, the white wire, because I can get to it easiest from here. And can you see around my hand there? Yes. And we can adjust our output voltage, just like we should be able to. So this part of the circuit is working. So without going any further, the only other possible scenario is that the pass transistor shorted. And I can see with the pass transistor is in there. I don't know which is the collector emitter base. Let's see. I have to think myself upside down here. It should be base collector emitter. So let's take a look at what we've got here. Okay, let's look at the base. And as I turn the potentiometer, I get from 10 to 21 volts. But let's look at the collector, which should be about should be our 22 volts at the collector. And there it is. Now the emitter should be based on the base voltage, but I'll bet I'm going to see the 22 volts on the emitter. And there it is. And that goes directly to the output. So there is pretty good evidence that my pass transistor is shorted. Okay, let's pull that circuit board out of there and trace it and draw a schematic of it and put those voltages we just found on the schematic and see if we can confirm that it was our pass transistor that shorted. Okay, so we took this thing apart. I drilled out the rivets that held the bracket in here that were holding the circuit board in, and the power cord fed through a little hole in the circuit board. I had to break that out. That's kind of crazy, but I guess it was just not really strain relief. We have strain relief right here. So, but nevertheless, it just fed through the circuit board. I took it apart and soldered everything. I have no intention of repairing this. We're going to try to figure out what went wrong. And if I do anything, I'm going to repurpose this into a better quality power supply. So I took it apart, flipped it over, traced the circuit board. This looks like it was done by hand. And here is the schematic. So we start with 117 volts input on the transformer, normal for the states here. 16 volts AC out. After going through the rectifier and filter, that would give us 23 volts DC. And we'll take a look at most of the circuit later. The one modification I made, though, is I cut the circuit here and then put in a potentiometer so that I made this a variable power supply. For more information, watch my videos on the linear power supply to see this. I'm not going to go into too much detail on things that I do in that video. So anyway, I just cut the circuit, added the potentiometer, and that goes and feeds the Darlington pair of the transistors. Now there's three components here that I would not have put in here. This 0.1 microfarad capacitor, this 2.2 microfarad capacitor, and this 2.1K resistor. We'll take a look at this in a few minutes and try to figure out why these parts are there. But right now, let's just dig right in and see if we can figure out what failed in the circuit. So let's take some of the clutter out so we can see what we're doing. So when I was checking the voltages there, unless you were watching very carefully, you probably didn't see what I was doing. So let's put those voltages up here as we examine what we did. So first I checked the Zener diode, and it came out at 15 volts. I said, well, that's a little high, but let's see if that's reasonable. So 15 volts into this Darlington pair. Are we expecting 12 volts out? Well, the standard rule of thumb is to expect 0.7 of a volt drop across each base to emitter junction. So we're going to lose about 1.5 volts. So start with 15 volts, lose 1.5 volts, we're down to 13.5 volts on the output. So yeah, okay, 13.5 volts, I can live with that. It's mainly designed to power things that were designed to be powered by a car battery, which can go up to 13 to 15 volts, so we're good there. But what about that assumption of 0.7 of a volt across each base to emitter junction? That's when the transistor is conducting a significant amount of current. If we have no current, we're going to get a smaller voltage drop from the base to the emitter. This light emitting diode is going to take maybe 20 milliamps or so. That'll put a little bit of a current through the transistors. And this 2.1K resistor, maybe that's there to give us a little bit of bias on there to get that get a little more voltage there. I'm not quite sure what that's there for. We'll try to figure that out in a few minutes. But the truth is, this power supply on a no load puts out nearly 15 volts. So we really don't get the 0.7 volts across these transistors at all. We get much less because they're just not really conducting a significant amount of current. That's the real world of transistors. Remember that 0.7 volts from the base to emitter of a transistor is a typical voltage. It's not etched in stone. And here's a case where it's actually considerably less. So it turns out to be about a 15 volt power supply at no load. But when we start to load it down, we will need more base current in the transistors to get more emitter current. That means that the base to emitter voltage will go up and probably pretty close to 0.7 of a volt. So once we load this down, we can probably expect about 13.5 volts on the output. So anyway, we have our 15 volts of the Zener diode, so that's not what failed. Let's say that Zener diode had burned open. So now we just have the potentiometer here, which is, what is this potentiometer? It's a 10K potentiometer. So now we have the 220 ohm resistor in series with the 10K potentiometer forming a voltage divider. And we have what? That's about a 40-to-1 ratio. So that means that we will have almost 98% of our voltage across the 10K potentiometer, which is going to give us pretty close to 22 volts there. However, the voltage is still going through the potentiometer, so we can still adjust the output voltage. So now we have a variable, unregulated, about 22 volt power supply. If I had not made the modification, then we would have our 220 ohm resistor going straight from the unregulated voltage to the base of the first transistor, and then that turns that transistor on, which turns the next transistor on. Then we would have our full unregulated voltage going straight to the output, which is the symptom we have. So actually our symptoms are not quite right for a burned out diode because we have that potentiometer there. But if we had the original circuit, the full voltage on the output would be a symptom of a burned open Zener diode. But we've already proved that the Zener diode is good. We have 15 volts there. We have good variable voltage coming out of the potentiometer, so we have to look elsewhere for the problem. The next thing to look at is this pass transistor shorted? Well, let's take a look at it. When I measured the voltage on the collector, I got 21 to 23 volts, depending on where I had this potentiometer. Why should that voltage on the collector be changing? Well, obviously we're getting a significant amount of current flowing through this 27 ohm resistor and getting some voltage drop as we adjust that potentiometer. So getting the current maybe through this 2.1K and also through this light emitting diode, enough to make a 1 volt difference depending on where we put that potentiometer. So I set the voltage at the potentiometer to 0 volts. That gave me 21 volts at the collector, 10 volts at the base, and 21 volts at the emitter. And with 10 volts at the base, I should have about 9.3 volts at the emitter. So there's something wrong right there. It looks clearly like it's shorted. When I turn the potentiometer until I had 15 volts on it, that put 21 volts at the base. I have 23 volts at the collector, 23 volts at the emitter. So in either case, I have the same voltage at the emitter as the collector. And generally, that tells us one of two things. Either we have a short circuit or no current. But this is a transistor, and the emitter voltage should be dependent on the base voltage, which should be approximately 0.7 of a volt below the base voltage. We look at the base voltage, it's 10 volts. The emitter voltage should be around 9.3 volts, and it's not. So obviously we have a shorted transistor here. But could the other transistor be causing the problem, or at least contributing in such a way that it's masking the real issue? Well, let's take a look at it. We have 0 volts on the base and 10 volts on the emitter. Is that reasonable? Well, it's a reverse bias junction, but not exactly. The base to emitter junction of a bipolar junction transistor acts like a Zener diode, and they typically have a breakdown voltage of around 5 volts. And the MJE31 is no exception. I looked it up. The emitter to base breakdown voltage is 5 volts. We have 10 volts here, so if it's looking like a Zener diode, it's looking like a burned out Zener diode. So the first transistor is a bad transistor. Could that be the whole cause? Well, we look at the base of the main transistor here, and it's 10 volts. The emitter is 21 volts. No, that transistor is clearly shorted, because with 10 volts on the base, we should have approximately 9.3 volts on the emitter. So the main transistor is shorted, and the other transistor was somehow taken out when the first one shorted. How could the first transistor have been taken out when the pass transistor shorted? Well, let's take a look at what we have here. It looks like a Zener diode. The Zener diode needs some current limiting. Yeah, we have some current limiting through the 10K potentiometer, so the pass transistor shorting should not have damaged the first transistor. But if I adjust that potentiometer all the way down to 0 volts, then I no longer have any current limiting. So I'm dumping the full unregulated voltage right into the emitter of the first transistor, and that goes straight down to ground, and it took it right out. So when the pass transistor went and I started fiddling around with the voltage control, it took the first transistor with it. So both transistors are bad. The first one died, took out the second one when I messed with the control, and that's what's wrong with the circuit. So now let's take a look at some of these components and see what they're there for that we don't talk about in the linear power supply video. First one is this 0.1 microfarad capacitor. And why is that there? So this capacitor goes from the collector to the base of this first transistor. The collector to base junction is reverse biased. And remember that a reverse biased diode has a P region, a depletion region, and an N region. And that means we have a conductor, an insulator, and a conductor. So what do we have? Two conductors separated by an insulator. We have a capacitor. So that reverse biased collector to base junction acts as a capacitor. Now normally the voltage at the collector is 180 degrees out of phase with the voltage at the base. But with this capacitor, that can be changed to be in phase, which means we have positive feedback from the collector to the base. So what do we have if we have an amplifier, which a transistor is, and we have positive feedback in that amplifier? We can get oscillation. So that tiny capacitance in that junction may cause this to oscillate at high frequency. So this 0.1 microfarad capacitor is in parallel with the capacitance of the junction, increasing the capacitance. And so any oscillations that try to start will happen at a lower frequency, which I'm assuming would be damped by all the filtering in the rest of the circuit. How about this 2.2 microfarad capacitor here? I think that's there as a filter, because when this is delivering a heavy load, we are going to get a lot of ripple on this part of the circuit here that goes to the collector of the transistors. So we have a heavy load, the capacitor is going to charge up to close to 23 volts. It might not be able to get all the way up if there's a lot of current being taken from it, but it's going to charge up and then it will discharge. And as long as that voltage does not discharge below the Zener voltage, so as long as it stays up above 15 volts, everything should continue to work. So the output voltage is going to be dependent on the Zener diode voltage and the two transistors, as long as the voltage doesn't drop down low enough that the Zener diode doesn't have enough voltage to work from. But what's going to happen is, as we get that ripple, those huge voltage fluctuations on the collector, that's going to change the voltage across our 220 ohm resistor, which means the current through it will change rather radically, which means our current through the Zener diode is going to also be radically changing. And Zener diodes are not perfect. They do fluctuate based on the current going through them, so as we get that high ripple, we will get a slight variation in the voltage across the Zener diode, which means the output voltage will change. I think this 2.2 microfarad capacitor is there as a filter to smooth out those variations and reduce the amount of ripple that happens at the Zener diode, and therefore reduces ripple on the output. The one component that really has me confused, though, is this 2.1K resistor connected to the base of the pass transistor. I've been trying to figure out why it would be there, and I can't come up with a good answer. It's something I'm just not familiar with. Maybe Dave Jones can tell us why it's there and tell me if I'm right about those two capacitors.
Hi Bob, your analysis looks pretty good on this thing, and I am also puzzled as to why this 2.1K resistor is here on the base of this Darlington pair like this. Now, this Darlington pair series pass transistor is effectively an emitter follower. It's just got more gain because it's in the Darlington configuration, and emitter followers are sometimes notoriously bad for oscillation with larger capacitive loads. And of course, with a power supply like this, you don't exactly know what the load's going to be. So as you speculated, that 0.1 microfarad there is likely for stability in that case, and also the 2.2 microfarad here is obviously going to reduce the ripple that you're going to see on the regulator, as you mentioned previously. So what is the job of the 2.1K here? Well, I've never actually seen it in that configuration before. I've never seen anyone actually pull the base of the actual pass transistor in a Darlington pair like that down to ground. So, but my guess is that it's a tweak to increase the phase margin of this whole circuit effectively, because when you increase your phase margin, you prevent oscillation. So of course, it would require a full, either a full simulation of this using the actual transistors, actually get models for the transistors and everything else, model it, and or build the thing up and actually do a proper sweep of it, a frequency response sweep. So that would be like very interesting to know whether or not it is in there. That would be my guess, is that they're like they're shifting the pole, increasing the phase margin, doing whatever, tweaking the thing, you know. Maybe they just picked the 2.1K value out of their hat. Maybe they just, you know, had the thing oscillate when they were developing this and went, oh, how can we shut it up? You know, let's just shove a 0.1 mic in there, and it's still oscillating under certain conditions. Let's, you know, look, if we shove a 2.1K here, it fixes it, and that's likely increasing the phase margin to prevent oscillation on the amplifier. That's my guess anyway. So without doing further simulation and or frequency response gain phase response testing, it's not easy to know, but that's got to be my best guess anyway. Thanks, Bob. See ya.
Thanks, Dave. I really appreciate you taking a look at the circuit for us. I guess that 2.1K resistor is just going to remain a bit of a mystery. There is one possibility I've thought of about why that might be there. When you use a transistor as a switch, to switch the transistor off, you drop the base voltage. And depending on what the load is, dropping the base voltage might cause that base to emitter junction to become reverse biased. And when you have a reverse biased junction, you have a capacitor. So now you have a charged capacitor at the base of the transistor that needs to be discharged before that transistor can turn off. And in the case of a Darlington pair, you might really deeply saturate that transistor, which means you have a lot more charge to bleed off than in other cases. So putting a bleed resistor on the base of the second transistor in a Darlington pair is common when you're using that as a switch. Well, that doesn't apply to the circuit, but it wouldn't be the first time that an engineer used an element in a circuit that he saw used somewhere before, but doesn't know why it's there, but thinks, well, it's in this circuit, so I think I need it in my circuit, putting it in there, not realizing that this element does not apply to his circuit. This is called cargo cult engineering, and it's based on cargo cult science. I'll put a link in the description below to an article on cargo cult science if you'd like to read where this term came from. So maybe it's there just because someone thought it needed to be there, but I don't think it does. So thanks again, Dave, and let's move on. The next component I want to talk about is this 27 ohm resistor. I don't use this in the power supply in the video series, but I do talk about it. This is a current limiting resistor. The idea is that as we take current from the power supply, that current passes through this resistor. And of course, as we have more current go through the resistor, we lose more voltage across it. So the idea is to choose a resistor such that at the rated current, we are losing enough voltage across that resistor that there's no longer enough voltage at the collector of the pass transistor for it to sustain the output. So let's assume that they're promising us the full 2.5 amps at 90% of the rated voltage of the power supply. So that's about 10 volts. The pass transistor is going to be saturated at this point because it's losing collector voltage and can't sustain the current that the HFE should be causing. So it's in a state of saturation. That means we'll have about maybe half a volt between the collector and the emitter. So 10 volts on the output, half a volt across the transistor. That puts 10.5 volts at the collector. So we have about 12.5 volts across this current limiting resistor. So at 12.5 volts at a rated current of 2.5 amps, we want 12.5 volts divided by 2.5 amps. That gives us a 5 ohm resistor. That's not a 5 ohm resistor. Okay, so what will that give us? So we want to lose 12.5 volts across the resistor. That's 27 ohms. 12.5 divided by 27 gives us 462 milliamps. There is no way this power supply is going to give us 2.5 amps. Even if we short the output, that's going to give us almost 20 volts across there. That's only going to give us about 800 milliamps, and that's with the output dead shorted. This isn't making a whole lot of sense to me at all. I think that should be about a 5 ohm resistor. That 27 ohm resistor is not going to work. I don't get it. Well, guess what? If you take a really, really close look at this resistor, you can see a tiny, tiny little speck just before the 2. This is a 0.27 ohm resistor, not a 27 ohm resistor. If we take a look at the amount of voltage we lose across that, though, at 2.5 amps and 0.27 ohms, we only lose 0.675 volts across it. That's not a lot of voltage to lose. Now, I calculated we needed a 5 ohm resistor to lose enough voltage at 2.5 amps to start limiting the current. Where could my thinking be wrong? Well, for one thing, I wasn't even thinking about power consumption. If we take that 5 ohms and 2.5 amps and use the I squared R formula, we find that we are going to consume over 30 watts. So we need a pretty hefty resistor at 5 ohms. So my thinking is wrong somewhere. My best guess is that they're assuming that when we are at the rated current at 2.5 amps, that we're sucking current out of that filter capacitor so fast that it really can't charge up much, and so the average voltage on it is much lower than I was assuming. So we don't need nearly as much resistance. I don't think there's really any way to calculate something like this. I think you'd have to do it by trial and error to find out just how much resistance you need to put here to increase the output impedance of the whole circuit so that the output voltage begins to collapse at the desired rated current. Well, anyway, that's it for this little autopsy video. I said I'm not going to fix this, but I think I've changed my mind, because I could replace both these transistors with a single power Darlington, and it would be trivial to bodge in a operational amplifier to this to make it a precision regulator. So stay tuned, and maybe we'll resurrect this power supply after all. And a big thank you to all of our sponsors and patrons at Patreon who are making all of this possible, and thanks to everyone for watching.